nice and talking.
When you're right.
All right, here we go. Dot product. So, let's talk about what you know. Okay. I'll put that over here. What you know right now. You don't need to write this down. You just need to tell me. What do you know how to do to vectors right now?
1 through 4.
Okay.
I know how to find
I've
the
done
dot
such a great
product.
job in helping you to give the names for it. Go ahead, Robert.
I know how to find the dot product.
You know how to, you don't know how to find the dot product.
I'll find
You
it
can
where-
feign ignorance here. Okay.
Wait, what's a dot product?
How to
Okay.
find the magnitude.
Okay, you do know how to find the magnitude of a vector. Okay.
I know how to find.
You know how to find the angle. We know how to have, if you've got the magnitude and the direction, you can break that down into its x and y, right? Can you add vectors together?
Yes.
Yeah, pretty much by doing that process. Break them down to the x and y, add them together, then put them back together, you know, Humpty Dumpty.
And can you multiply?
That's a good question.
Great.
I think we can add vectors. If you have vector A and then you have vector B, you can add, you don't need to write this down, I'm just showing you. Add vectors, right? Amy, can you subtract vectors?
Yes.
How do you subtract vectors?
You just have a negative.
A, guys. Dominic, keep talking. Make me think you're not listening. Okay, I need you to listen. Thanks. Subtracting vectors, yeah, you just write that as A plus negative B, so B in the negative direction. And that corresponds to, you know, if this is A and then negative B would be kind of in that direction. And we've got a physical representation of what that means as well. But then that leads us to the question we can add, we can subtract. Dalton asked me to go, can we multiply vectors? And the answer is, yeah, you can, but like what part? Because you've got the magnitude and the direction, or you've got the x and you've got the y. And so what does that mean? Which part do I multiply and how do I do all that stuff? And then like just those operational knowledge, like what do I do? And then there's the added bonus question that's really important is like what does that mean? Or what does that tell me? Okay? With adding and subtracting vectors, adding them means, well, if you had a force that was pushing this way and also another force which is pointing in this direction with this magnitude on the same object, then the path that the object would actually feel the force on would be this right here, okay? But what does it mean to, when you multiply vectors, what do you get? Do you get another vector? Do you get a number? Okay? By the way, does anybody remember when you had like a vector which was 2 pieces of information, then we had previously 1 piece of information. Does anybody remember what we called that? A scalar. Yeah, when you just have like 7, okay, that's called a scalar. But if you have 7 miles at 30 degrees, then that's your vector, okay? So we are going to be talking about multiplying, hence the word product in today's lesson, okay? So here's how you multiply vectors. Here it is right here. Vector A, I'm going to use the dot as our multiplication symbol, hence the dot product there. And if you have 2 vectors, multiplying them, the dot product, it's literally this. It's the x component of A times the x component of B plus the y component of A times the y component of B. Now anytime you multiply 2 things, you're going to get a number. Anytime you multiply these, you're going to get a number. Then you add them together, then yeah, so this type of thing that you're going to get is literally just a number. The dot product is a number, also known as a, Preston? Scalar. So the dot product results in a scalar. Let's do an example here. Oh, Mr. Greensword, would you mind pulling up download vectors 5 and then pull it up there? Thank you. Let's say vector A, I'm going to give it to you here in component form, 2, 3. Vector B, I'll also give that to you in component form, 10, 6. So applying the dot product formula here, A dot B would be 2 times 10 plus 3 times 6. So 20 and 12, so 32? No,
38.
38. Once again, that's a scalar. I don't feel like we need to do a ton more examples of that. Are you okay with that? Okay, great. So, question. What does that mean? What does it mean? What is it good for? Does a big number mean something and a small number mean something else? Can you have negative numbers? Yeah. Can you have 0? Yeah. Well, it's important. And one of the things that it tells us is something to do with whether or not those two vectors are perpendicular to each other. Okay? So in other words, I mean, obviously, one vector could be going here, one vector there. Yeah, clearly they're perpendicular. But what if this one is kind of at an angle like here, and this one is kind of, it's possible for those to be perpendicular as well, right? Or anywhere around. I mean, you could have one of them kind of like this, and another one. Well, that doesn't look very perpendicular. Maybe like that. Move it up. Anyway, let's think about perpendicular vectors. So it's sort of a roundabout answer. Consider two perpendicular vectors. You all remember the perpendicular symbol, right? It's an upside down capital T. So here's vector A, and I'm going to call that, well, once again, 2, 3. So that's going to be over 2, 1, 2, and up 3. 1, 2, 3. And a vector which is perpendicular to that. Vector B. We're going to have to build this one because I don't know exactly what. What's the slope on this one? What's the slope of vector A? Slope of A.
3 over 2.
3 over 2. Now, going back to
Negative.
algebra, alright, what's the slope? If you have two lines that are perpendicular, well, let's go with the easy one. If they're parallel, what's the relationship with their slopes?
Same.
Same slope. But if they're perpendicular,
Negative reciprocal.
the negative reciprocal, or the opposite reciprocal. So if this has a slope of 3 over 2, then this one over here would have a slope of negative 2 over 3. I'm going to push that negative up to the top. So that's the rise. This is the run. So a run of 3, 1, 2, 3, and a rise of negative 2. So I'm actually going to go down 2. So 3 and negative 2. If I superimpose this one over here, hey, look at that. It's kind of cool. Right, those do look perpendicular, don't they? All right, so the component form here is 3, comma, negative 2. I wouldn't expect you to kind of know this. This is sort of like a contrived example to kind of show you what the answer is as relates to the dot product. But anyway, here we go. Let's calculate in this particular example where we know that A and B are perpendicular. What is A dot B? All right. Well, it's going to be the x. So 2 times 3 plus 3 times negative 2. x's and the y times each other, the y's times each other, and added it up. So you have 2 plus 3, or 2 times 3, which is 6, plus 3 times negative 2, which is negative 6. Yeah, wow, that's 6 plus negative 6, that is 0. That's kind of interesting. This would lead me to think that the dot product of perpendicular vectors is always 0. Okay? But I'm hesitant to make that sort of jump. So we'll do it generically really quickly, and then we'll see if we're right or if that was just sort of a coincidence. So let's say I've got vector A, which has AX and BX, or sorry, AX and AY. And now let's consider vector B such that B is perpendicular to A. Alright? Well, we saw that, generically speaking, vector A is going to be kicked over AX and kicked up AY. So the slope of A is going to be AY over AX. Generically. The slope of B, since it's always going to be perpendicular, since I've declared that B shall be perpendicular to A, is the opposite reciprocal of A. So call out to me with the slope of B. Negative AX over AY. That's the rise. That's the run. So the run corresponds to whatever's in the X position. So we've got AY right there and negative AX right there. So now, in my generic vectors, the dot product, A dot B, that's not really very easy to see. That's going to be AX times AY plus AY times a negative AX. Y'all agree with that? And then here we have AX times AY minus AX times AY. Mr. Greensboro, you might run to Miss Bailey, see if she's got it.
She said that not to come to her again. Yeah, but I think I might can't find some.
Yeah. Oh, there's one over there. Anyway, AXY minus AXAY, that's going to be 0. Ooh, there's a blue one right next to you. Would you mind handing that one to me? What about this guy? All right. Ooh, that one's a little better. All right, it's 0. Conclusion. We'll write it on the board of conclusions. If vector A dot vector B equals 0, then what, class? If their dot product is 0, then they're perpendicular. Then A is perpendicular to B. There's a few more things the dot product can tell us. One more thing. The dot product can tell you the angle between two vectors. So for instance, if I have vector A right there and vector B, I put them both at the same initial point, and there's angle theta in between those two. Then with this formula, which we'll prove later, it uses something called the law of cosine, which we haven't discussed yet. We'll tell you what that angle is. Here we go. Cosine of the angle in between them is equal to the dot product of the vectors divided by the product of the magnitude of the vectors. Cosine theta is equal to the dot product divided by the magnitude of the products of the vectors. If you say, that's great for telling me that the cosine of the angle is this, what if I want to find the angle? Well, that's no big deal, you just do inverse cosine. So theta is the inverse cosine of all of that. A dot B divided by magnitude A, magnitude B. That's a formula worth writing down. A couple of other just short notes, sort of vocabulary terms that we're going to see here in a minute. The word orthogonal means perpendicular. So if you have two vectors, if they're orthogonal, that means that they're perpendicular. Okay, that is, they would be perpendicular if you were to attach them at the same spot. You know what I mean? You could have a vector over here, and you could have a vector over here, and you're like, are those perpendicular? And somebody somewhere, you know this type of person, be like, no, they're not perpendicular, because perpendicular means that they have to be touching, and those are not touching, so therefore they're not perpendicular. You're like, all right, you little turd, you know? If you connect them together, if you draw them at the same spot, then they would be perpendicular, okay? All right? So, yes, they are perpendicular. You're like, well, no, the technical term is they're orthogonal. Okay, fine, they're orthogonal, all right? So anyway, the technically correct term is that those are orthogonal, but I'd say they're perpendicular. Another thing that we're going to need to know just to be successful on this homework is to know when two vectors are parallel, okay? Two vectors are parallel if their components, I mean, you could say if they have the same slope, which would be fine, are multiples of each other. I could also say if they point in the same direction, they're parallel. Let me give an example using our classic 2-3 example. So here's vector B, 2, 3. So up to, across 2, up 3. And then you've got vector W, which is 4, 6. Alright? So that goes across 4 and then up 6. They're both pointing in the same direction. If you take this one, it'd be still right. It'd be, you know, over 2, up 3. Because if you did another one, it'd be over 2, up 3. You're still on the same line. Okay? So here, the 2 times the 2, you know, double the 2, you get 4. Double the 3, you get 6. What might be another vector that is also parallel to those vectors?
6, 9.
6 and 9. What about 20, and 30. Multiply this by 10, multiply this by 10. Just scaled up. So we would say that those two vectors are parallel. Okay? That's enough for you to take care of vectors 5. Y'all may want to take care of vectors 5 or take care of vectors 4, I don't know. I'm going to take one, pass it down if you don't mind. Hey, you can how do I move this thing?
Oh. I didn't download it.
Is there a special pen? What do I have to do by hand?
Yeah, I don't know.
Oh, you do that? I'm just saying, I mean,
Try it now.
it's not. No, I'm just joking with you. We still have the old one. I thought yeah, we're good.
Oh yeah.
It's not, I'm not trying to get you, I played myself on that one. All right, so here we go. Y'all have it. Number 1, given the vectors v, negative I plus, or sorry, minus 8j, and w, negative 6i plus 5j, find v dot w, okay? Well, you're like, oh, Mr. Goddard, it's not in the component form, right? It's not in the angle brackets. Okay, big deal. Do you know how to get the angle brackets from this? What's the x component here, class, on v? Negative 1. What's the y component? Negative 8. What about over here? And here? 5. So v dot w is going to be negative 1 times negative 6 plus negative 8 times 5. So 6 minus 40 and negative 30, that's looking right? Negative 34?
Yep.
Not too bad. So that is finding the dot product of two vectors given in AI plus BJ form. Number 3, finding the dot product of two vectors given the vectors in component form. Dominic, talk to me. What would on number 3, how would I find that dot product? Or give me the expanded application of the formula here.
Well, since we already have it in front of what we did last time, just 1 second.
Yep, so go ahead and call that out to me.
So you do -8 and 9, 5, and 6.
And between them? Adding, yep, that's the formula. What do y'all calculators say? I hear negative 42. Negative 72 plus 30, that seems about right. Guess I have to erase it down. Anybody still need that? We should be good to go. Let's look at number 5. Complete the following for each pair of vectors. Do not round any intermediate computations. Okay. First, it says let W equal negative 9i plus 7j and R equals 7i plus 5j. Find the angle between W and R. Okay, good. This is this formula right here. Theta equals inverse cosine A dot B magnitude A magnitude B. Okay? I might kind of do some of this stuff piecewise, right? Sort of in pieces. So first thing, yeah, go ahead and scroll down just a little bit more at the end of the. Okay. So first off, I might find W dot R. So that's going to be negative 9 times 7 plus 7 times 5. good on that? I need a number, folks. -3, 5. Go. 3, 2, 1. We got Preston.
-28.
All right, -28. Do I have agreement from the audience?
Yes.
Okay. By the way, I'll write off here to the side here so we can know where we're going. We're doing theta equals inverse cosine of W dot R divided by magnitude of W times the magnitude of R. I found one piece of the puzzle. W dot R is -28. Now I'm going to find magnitude of W. And if you remember, magnitude is the square root of the sum of the squares. Okay? So that's going to be square root of -9 squared, so 81. Or do you want me to write it down? So -9 squared plus 7 squared. I'm actually not going to type that whole thing into the calculator. I'm just going to leave it as the square root of, now wait, y'all do, what is 81 plus 49? 130? I'm just going to leave it as the square root of 130 and put that over here. Because I'm not rounding any intermediate calculations or computations. That is definitely an intermediate computation. And then if I follow that same sort of process, the magnitude of vector R is square root of the sum of the squares. We found to be a Pythagorean theorem. So 7 squared plus 5 squared. So 49 plus 25. Say again? 74. All right. So make sure your calculator is in degree mode since they're asking for our answer to be in degree. And inverse cosine, -28 divided by square root and square root. Make sure you've got that whole denominator in parentheses because we want to make sure it's -28 divided by that whole thing. Otherwise, it's going to give us something kind of strange. And I'm going to need an answer and someone else to verify it. Round to the nearest degree, yeah.
I got 107.
I'm hearing 107, but I'm going to need to. But you're at the same table, so that only counts for a half there, Preston. I'm going to need someone from another table to verify. She got 107. Someone from over here, from this 2/3 of the room.
Do you round it? Let me see.
Give it a shot. Inverse cosine.
I did something wrong. I'm so out of it right now.
It's 74, not 79.
Divided by, and then put it open parentheses right there, since we're going to do all kinds of weird stuff. Square root. Close that, yep, and then another square root. 74. Hit your remote button real quick. Here's your remote. Yeah, what would you wrong? Go back to your white.
You got 107? Yeah.
-28.
I actually got positive. I put positive.
Anybody got like 70s?
I got 106. 107.
Did you type in -28?
I put it on.
Oh, no.
That, and Taylor, that was all. You got 107. Okay, 107 is the correct answer. I typed it in with Taylor, and we got like 70 something. But that's because I didn't see the 28 there. All right, 107 is the correct answer here. So that's the angle between them. So are they parallel? What would the angle between them be if they were parallel?
90.
Parallel? Zero. The parallel, there's zero. If they were orthogonal, then you'd be 90 or something, yeah. And so this looks like a neither. Number 2. Anybody wanna, number 2, I'm looking at that one and my experience says, I'm just gonna draw that one. I'm gonna draw that one. What does this one look like? T is negative I plus J. So that's a -1 and a +1. So what would that look like? So to the left and up. Okay. And then this one is
To the left and down. Oh, is trying to move.
alright. And then over here to the left, that's -1 and 1 and down. That I'm really thinking that this one's gonna be orthogonal. But I'm not totally sure. So let's go ahead and work it together. Let's see what we get. So let's first off do the dot product. So T dot V. So that's going to be -1 times a -1 plus a 1 times a -1. So -1 times -1 is, and then plus 1 is, that's plus a -1. So 1 minus 1, so that is 0. Oh! Dot product is 0. That means they're perpendicular. They're orthogonal. We're done. We got this, right? The angle between them, 90 degrees. They are orthogonal. All right, that was nice. Everybody see what we did there?
Yeah.
You're probably gonna have something nice like that happen on some of your homework problems, hopefully. Hopefully not the crazy ones. Go ahead and scroll down there one more there. Next page. So you always want to look for some easy things like that. I'll tell you right now, one of these two have something kind of interesting about it. Oh, parallel. Which one? Number 1 over here, part 1?
Multiple by 3.
Ah, 3 times 3 is going to give you a 9. 2 times a 3 is going to give you a 6. Absolutely. So these are parallel. And what is the angle between them? 0. Yeah, it's going to look at 7 minutes ago. -9 minus 5j, -9 plus 4j. Oh, that seems like if it was a +5, we might happen. But yeah, what I want you to do is, as a table, I want you to solve for the angle and then tell whether it's parallel, orthogonal, or neither. And it's neither. Okay, so you got to do the long way on this one. So go through that previous process. When you get it, raise your hand, wave at me, and I'll give you a thumbs up, and then you'll have any remaining time to take care of what you want to. Today we talked about the dot product. This homework is due on Friday.